Good morning, friends. So today we are going to discuss about the hydroelectric power plant. So in the hydroelectric power plant, we are going to learn about the hydraulic turbines. Hydraulic turbines. So we may discuss the class. We are going to discuss about the classification of hydraulic turbines, and we are going to see the pelton wheel turbine, Francis turbine, and Kaplan turbine. Wait a minute. So this is about layout of hydroelectric power plants. This is about the layout of the hydroelectric power plants. So here we need to construct the dam to dam is constructed across the river for storage of the water. So here we have a large diameter of pipe, so that we call it as a penstocks. So through these pipes, the water will be flowing. Through this pipe, the water will be flowing. So this is about. So here we have a dam. So dam is constructed across the river for storing of the water. So here, large diameter of pipes that we call it as a penstock. Penstocks will be connected here. So through these pipes, through this penstock, the water will be passing through this penstock. So here, a powerhouse with the pumps and turbine. So turbines will be located here. So here, the hydraulic machines, which converts the hydraulic energy of the water, hydraulic energy will be converted as the mechanical energy. Further, it will be converted as the electrical energy. So here, the hydraulic energy will be converted into the electrical energy by using turbines. So the hydraulic machines which converts the hydraulic energy, it will be converted to the mechanical energy. Further, it will be converted to the electrical energy with the help of generator will be coupled with the turbines. So here we have a head race level and tail race level. So the water will be discharging. After striking of the turbine, the water will goes to the tail race. So here we have a head, and then some losses will be there due to friction. So net losses due to friction will be there. Head loss due to friction. So this is about uh, hydropower plant layout. So the concept of the hydropower plant layout is, so here the water will be storing, dam is constructed for here, the dam will be constructed here. So the water will be storage purpose, storing will be there. So from this constructs large diameter of pipes will be here. Through this large diameter of pipes, the water will be flowing from this penstock to this turbine. Then this, at the end of the penstock, we have a nozzle will be there. At the end of the penstock, we have a nozzle. So from the nozzle, the outcome of the nozzle, we call it as jet. So the jet of water will be striking on the turbine vanes. The jet of water will be striking on the turbine vanes. So after striking of the turbine, the water will goes to the tail race level. The water will be discharged to the tail race. So now we are going to see the turbines. So a hydraulic turbines, which converts the potential energy of water into the mechanical energy, which is done to utilize the run of the electrical generator to get the electricity. So the water energy will be converted, the hydraulic energy will be converted into the mechanical energy. Further, it will be converted into the electrical energy. Finally, we'll get electrical energy. The hydraulic turbine, which converts the potential energy of the water into the mechanical energy, which is done, it is utilized to run as an electrical generator to get the electrical energy. So now we are going to see the classification of the hydraulic turbines. So four categories. In the four ways we are going to classify the hydraulic turbines. First, according to the water available energy at the inlet of the turbine. The available energy at the inlet of the turbine. So here we are going to see the impulsive turbine and reactions turbine. So in the impulsive turbines, the available energy will be only the kinetic energy. We need to consider the atmospheric pressure. Pressure energy will be considered as a atmospheric pressure. So the available energy at the inlet of the turbine is only kinetic energy, that is about impulsive turbines. So the energy will be the pressure energy will be considered as a atmospheric pressure. So the pressure energy will be converted into the mechanical. The kinetic energy will be converted into the mechanical energy in case of impulsive turbines. So here we are using the nozzles. In case of reactions turbine, reactions turbine require a low head and a high rate of flow. In the reactions turbine, both pressure energy and kinetic energy will be converted into some useful mechanical work. So both pressure energy and kinetic energy will be converted into some useful mechanical work. So this is about the reactions turbine. So first classification according to the available energy at the inlet of the turbine. Second category, so according to the name of the originator, Pelton Francis Kepler turbine. Then third one, according to the action of the water, according to the action of water on the moving blades. Then according to the direction of flow through the runner, according to the direction of flow through the runner, tangential flow. So the best example of the tangential flow turbine is the Pelton wheel turbine. The best example of the Pelton wheel turbine is the tangential flow. So tangential flow. We may the tangential flow turbine we may observe in the tangential flow in this Pelton wheel turbine. Then we have a radial flow. Then we have a axial flow. Radial flow is the Francis turbine is the example of radial flow turbine. So spiraling action will be taken place radially. The flow direction of flow through the runner will be so the runner the flow will be goes to the runner is radially. That is about the radial flow. So that is about Francis turbine. Then axial flow, we have a along the axis. The direction of flow through the runner is along the axis. That is about Kepler turbine. Axial flow. A best example of the axial flow is the Kepler turbine. Then we have a mixed flow. So that is about radial flow turbine. Mixed flow turbine is a radial flow turbine. Mixed flow, the best example is a modern Francis turbine. So it enters radially and exit axially. So both flows will be there. Enter radially and leaves with the axially. So that is about a mixed flow. We have both radial flow and axial flow will be there. Enter radially and leaves with the axial flow. So that is about the modern Francis turbine is the example of mixed flow turbine. Then we have a according to the deposition of the turbine according to the specific speed. Then we have a according to the head available of the turbine according to the head. So I head power plants 100 meters and above. So this is about the available energy head available at the power plant. That is about another classification of the turbine is due to the, according to the head available. So in the high head 100 meters and above, then medium head 30 to 500 meters, low head that is about 20 to 50, 25 to 80. So the low head the best example of the low head power plant is the Kaplan turbine. So this is about so now we'll see one by one. According to the specific speed also we need to classify the turbines. So here we are going to see the one of the turbine that is about the impulsive turbine, the available energy. So the available energy at the inlet of the turbine is only kinetic energy. So here we have a nozzle. So we are using nozzles. In the impulsive turbine, we are using the nozzles, whereas in the reaction turbine, there is no nozzles. So here, the outcome of the nozzle we call it as a jet of water. The outcome of the nozzle we call it as a jet of water. So this jet of water will striking on the turbine vanes. So this rotating part of the turbine we call it as a runner. The rotating part of the turbine. So impulsive turbine, that is about Pelton wheel turbine. Now we are going to discuss the construction and working of the Pelton wheel turbine. So in the Pelton wheel turbine, so we have a runner. The rotating part of the turbine we call as a runner. So the shape of the buckets or vanes is a cup or double hemispherical shape. You may observe in this diagram. cup or hemispherical shape, bowl shape, cup or bowl shape of hemispherical shape will be there. So the periphery of the runner, we need to mount the buckets. The rotating part of the turbine, we call it as the runner. The rotating part of the turbine is called as a runner. So then we have a jet of water, nozzle and spear arrangement. So you may observe here nozzle and spear arrangement. This is about nozzle, and inside of the nozzle we have a spear rod. So this is about penstock, large diameter of pipes. We call it as a penstocks. So the water from the headrace level, it will be full. So the water will be headrace level, will be entering into this penstock. So the water will be passing through the penstocks. So at the end of the penstock, we have a nozzle. At the end of the penstock, so suddenly cross-sectional area will be decreasing. So the outcome of the nozzle we call it as a jet of water. Jet of water. So this jet of water will be striking on the turbine vanes. This jet of water will be striking on the turbine vanes. So here, the angle of deflection, the angle will be the shape of the shape of the vanes will be cup or hemispherical, symmetrical axis. So here, the jet of water will be striking on the this midpoint, particularly this midpoint. Angle of deflection maybe 150 to 165 degrees will be there. So it will be hitting symmetrical axis. So this jet of water will be striking on the buckets. This jet of water will be striking on the vanes. Then this runner shaft will be the runner shaft will starts rotating. That means it will be whenever the runner will be running, runner shaft will be rotating. That means mechanical energy will be developed. The mechanical energy will be developed. So here we have a more four components will be there: nozzle and spear arrangement. Then we have a casing, nozzle and spear arrangement, casing, a runner with the vanes, and we have a, bucket braking object. One more component is braking object. So these are the four main components. So first, so we need to regulate the flow with the help of nozzle and spear arrangement. We need to regulate the flow with the nozzle and spear arrangement. In this nozzle, we have a spear rod will be there. So whenever the spear rod will be operating by manually or by using power, so it will be pushing towards. So whenever we need to reduce the speed, whenever we need to regulate the flow, so this push rod, this spear rod will be pushing towards right side, will be flowing like this. So it will be obstruct the flow. It will be obstruct the flow here. Will be whenever it will be moving towards forward, whenever it will be moving towards right side, it will be obstructing the flow. So in this way, it will be regulating the flow of the fluid. It will be regulating the flow of the fluid. So whenever we need high speed, it will be the spear rod. It will be pushing towards backside. It will be come back to its original position. Then flow will goes on increasing. Whenever the flow will goes on increasing, so the rotating of the shaft will also goes on increasing. It will be generating more power. So here nozzle and spear arrangement. In this spear arrangement in the nozzle, it will be controlling the flow regulation, flow regulating. So by using spear rod, it will be moving towards forward side and to and fro motion. It will be moving towards right side and left side. So it will be regulating the flow. So here the flow will be this jet of water will be striking on the turbine vanes or buckets. The jet of water will be striking on the turbine vanes. The periphery of the runner, the symmetrically equi-shape. So the vanes will be mounted on the periphery of the runner, right? It will be placed symmetrically. So for creating more, developing more energy, we need to place symmetrically. So here the rotating shaft of the runner, the rotating shaft of the turbine is called as a runner. So the runner will be rotating. That means it will be generating mechanical energy. So here in the turbine shaft is directly coupled with this runner. So that further mechanical energy will be converted into the electrical energy by using generator. This generator will be coupled with the turbine shaft that is about runner. So then it mechanical energy input as the generator, then output of the electrical energy by using generators. Then we have another component that is about casing. Casing. So it will be preventing splashing, escaping of the water. It will be preventing the accidents. It will be preventing the accidents. Splashing of the water. It will be preventing the splashing of the water. It will be preventing the accidents. Unfortunately, any human beings or animals will not enter into this turbine house. So we have a casing will be there, preventing the accident. Then we have a braking object also there, braking object. So this is about the braking object. So whenever we need to shut down this power plant, so we need to supply in a reverse direction. The it will be indicating the reverse direction. So that will be it will be indicating the reverse direction. So the jet of water will be due to the inertia forces. It will be starts rotating due to that inertia. So we need to shut down the plant. The We need to break the jet. We need to break the jet. So these are the more four important components: the impulsive pelton turbine. So nozzle and spear arrangement. First one is the nozzle and spear arrangement. Second one, a runner with blades. Third one, casing. Fourth one is braking object. So these are the four important components in the pelton wheel turbine. Pelton wheel turbine. So the jet of water will be striking on the turbine. The jet of water will be striking on the turbine. Then the runner starts rotating. So it will be generating the mechanical energy. Further, this turbine shaft will be coupled with the generator shaft. Then further it will be converted as the electrical energy. So this is the main events in the Pelton wheel turbine. Pelton wheel turbine is the high head turbine. Pelton wheel turbine is the high head. It will be suitable for high head turbine. The flow will be tangential flow turbine. So tangent, the flow will be tangential flow. We need to play like this tangential flow. We need to place multi-jets also. We need to place multi-jets also. So this is about tangential flow turbine. This is about tangential flow turbine. I head turbine, tangential flow turbine. Then we have a I head tangential flow turbine. Then we have a specific speed of the turbine, and it will be low discharge. Pelton will be suitable for I head and low discharge. Requires high head and small quantity of flow. That is about Pelton turbine. So now we'll move the Kaplan turbine. So in this Kaplan turbine, this is about the low head. So low, it will be suitable for low heads. Kaplan turbine is suitable for low head. So here we have a boss. We have a So in this Kaplan turbine, we have a turbine shaft that we call as a hubbar bars. 4 to 8 vanes are mounted. So it will be fixed and guide vanes. Movable, adjustable vanes will be there. Adjustable vanes, 4 to 8 blades will be mounted on the periphery of this shaft hubbar bars. We call it as hub or bars. The vanes will be fixed like this. The flow will be along the axis of the shaft. The flow will be, so this is the turbine shaft, axis of the shaft. So axial flow. This is about axial flow along the axis of the turbine. The direction of flow through the runner is axial flow. So axial flow will taking place. The flow will be axial along the axis. So here we have a guide vanes. So in the Kaplan turbine and Francis turbine, there is no nozzles. So these are the reactions turbine. Both pressure energy and kinetic energy, will be converted into some useful mechanical energy. So here the guide vanes will be adjusting. Guide vanes will guide the flow to this runner. Guide vanes will be adjustable. These guide vanes will be guiding the water to this runner. So we have a casing. So this the water from the penstock will be enter into these guide vanes. Guide vanes will guiding the water to this runner. So here the rotating part of the turbine is called as a runner. You may observe in these diagrams. So one more important component of the striking of the turbine. So here both the pressure energy and kinetic energy in the reaction turbine, both pressure energy and kinetic energy will be converted into some useful mechanical energy. Both Total pressure energy, it will be converted into some useful mechanical energy. So here, so due to the negative pressure, cavitation will take in place in the reaction turbine. Cavitation due to the negative pressure, so the bubbles, what bubbles will be formed due to uh, the phenomena of formation of bubbles will be taken place. So that we call it as a cavitation. So due to the negative pressure, so formation of bubbles will be the phenomena of formation of bubbles will take in place. So we need to avoid that cavitation. So we need to use in the reaction turbine that is about draft draft tube. So this is about draft tube. So gradually area will be goes on increasing. Gradually area will goes on increasing for increasing the pressure. For increasing the pressure, we need to use draft tubes in the reaction turbine. Draft tube in the reaction turbine. So I hope you're understanding the concept of Kaplan turbine and reaction turbine that will be used in the hydropower plant, hydroelectrical power plant.